What's up? So in this video, I will be explaining Bayes' theorem. And the reason for that is I just did an online assessment. And let's just say there was a couple Bayes' theorem questions. So I'm very glad that I studied that um, in the past. Okay, so Bayes' theorem states that the P of, God, my handwriting, P of A given B is equal to P of B given A times P of A over P of B. All right. Now, let's just do like a quick proof of this because it really is a restatement of common sense. So when we have, why is that thick? When we have PA and PB, we can say that is equal to PB, PA. And this is the same as saying PAB equals PBA. Now, what is another way to write PAB? It's P of A given B times P of B. And what's another way to write P of BA? It's P of B given A times P of A. I think you can see where this is going. So let's just divide both sides by P of B, and then we get P of A given B equals P of B given A times P of A over P of B. Yeah, so that is a very short run through of proving Bayes' theorem. Now let's get into a practice question. So I'm gonna type this out, and how do I get rid of this? All right, whatever. So this is a very common question in like quant style interviews. Let's say, let's make this. Um, you have two coins. One is biased and lands heads 9 out of 10 times. The other is fair and lands heads half of the time. They look identical. All right. Now let's say you pick one of the coins, flip it 5 times in a row, and it lands heads every time. What is the probability that you picked the fair coin? Wow, that looks so ugly. Can I change it? No. All right, whatever. Okay. So to solve this problem, I'm going to establish two events. One is A, which is you picked fair coin, and B is going to be 5 heads in a row. So we want to find P of A given B. And from our earlier discussion, we know that P of A given B is equivalent to P of B given A times P of A over P of B. Now, it looks super straightforward when you put this formula right here, but let's think about what information we actually have. So the chance that you picked the fair coin, well, you have two coins. One is fair and the other one is not fair. So really you have a 1 out of 2 chance picking the fair coin, right? So we can plug that into the equation later. Um, and what is the probability of getting 5 heads in a row given a fair coin? Well, that's going to be P given A is just a standard 1/2 to the power of 5. So 1 over 32. So now how do we find the probability of getting 5 heads in a row not knowing like the coin? What I am going to do here is actually draw a tree. The first layer is going to be A and A complement. So A complement would be the coin is not fair. So it's the biased one. And then we're going to draw B and B complement. So we already know that the probability of B given A is 1 over 32. The probability of A is 1/2. So given that A and A complement are mutually exclusive, we can say that probability of A complement is also 1/2. And then we also use mutual exclusivity, sorry, to say that here the probability of B complement given A is 31 over 32 because these two need to sum to 1. All right, so what's the probability of B given A complement? Or in other words, what's the probability of getting 5 heads in a row with a biased coin that lands heads 9 out of 10 times? Well, it's 9 over 10 to the 5th. And low-key, I'm not built like that, so I don't know the exact like fraction simplification. But that's fine. I'm going to use some Desmos later. And then with mutual exclusivity, we know that this is equal to 1 minus this quantity. All right. So now we know that like in this probability space, we can just find the probability of both B's happening, if that makes sense. Both routes. And sum them. So we can say probability of B is equal to probability of B given A times probability of A plus probability of B given A complement times probability of A complement, or BA, probability of PBA plus PBA complement. Now, we can get these by multiplying B given A with, B given A with A. So we are going to get 1 over 32 times 1/2. And we're also going to get this fancy number also times 1/2. Cool. And just open Desmos and see what's up. So we had 1 over 64. I'm just going to simplify the left fraction a bit. Yeah, so we get this number. Shoot, maybe I picked some bad numbers, but whatever. 31087 over 100,000. What a beautiful number. So now we have probability of B, and we have found every number in this formula, so we can get probability of A given B. So let's uh, just for myself, actually, no, let's use a different color now. So P A given B is equal to, let me make some more room. P of B given A times PA over PB. And we have found that this number is PB. So 31087 over 100,000. And then P of B given A, let's remind ourselves, it's getting 5 heads in a row given you're using a fair coin. So that's 1 over 32 and 1/2. And in general, with these simple Bayes theorem questions, you're going to notice a pattern that when you're finding the probability of B, or like you're finding the denominator, you're going to sum like 2, maybe 3 terms. The first term, or not the first term, but one of the terms is most likely going to be your numerator, right? So yeah, just a pattern I've noticed from practice problems. So let's put this into Desmos and see what's up. We get 0.05. Let me use a new color. Or it's not equal to, it's about 0.05. And there was like a 2 somewhere, right? Yeah, 2.6. Okay, so 3. So that is the probability that you picked the fair coin, given the fact that you just flipped 5 heads in a row. And that kind of makes sense when you think about it. It's like you got 5 heads in a row and you're either using a fair coin or a bias coin. It's most likely going to be the bias coin. So yeah, that's a very quick run through of a Bayes theorem proof and practice question. Thanks for watching.